Section: Introduction. In this section, we introduce the concept of Foley design, a vital aspect of filmmaking that has been around since the 1920s. It involves adding sound effects to silent films and videos to enhance the audience's experience. Typically, Foley sounds are created by individuals mimicking real-life sounds, like using thin metal plates to replicate thunder or squeezing cornstarch in leather to imitate footsteps in snow. This process is time-consuming and requires skill. With the rise of video generation technology, designers can now easily create video clips. However, many of these generated videos lack sound, which reduces their appeal. To address this, automatic video Foley technology has gained attention in both research and industry. Recent advancements in latent diffusion models, LDM, have led to promising methods for generating content, including text-to-image, text-to-audio, and video-to-audio generation. Despite the progress, video-to-audio generation still faces challenges. First, we need to ensure that the sounds generated match the video's content, like avoiding dog barks in a cat video. Second, the sounds must be synchronized with the video's timing. Third, we must consider loudness consistency, as sounds should match the appropriate intensity levels in the video, such as an elephant's footsteps getting louder as it approaches. To tackle these challenges, recent studies have tried to align sounds with video content using visual features. However, these methods often generate audio from a single video without allowing for control over timing and loudness. One approach, Sonic Vision LM, considers timing but overlooks visual perception since it only uses text prompts. The issue of loudness consistency has received less attention and needs further exploration. In our work, we propose a more controllable audio synthesis framework called Draw and Audio, which effectively addresses content, timing, and loudness consistency. Draw and Audio can generate audio based on multiple inputs, including video, text, drawn video masks, and loudness signals. We introduce the Mask-Attention module, MAM, to improve the consistency between the generated audio and the input video by focusing on specific areas of interest. Additionally, we implement the Time-Loudness module, TLM, to ensure that the audio maintains both timing and loudness consistency. TLM allows for hand-drawn loudness signals as input, enabling us to create audio with specific loudness variations. To train TLM, we developed an algorithm that combines root mean square and exponentially weighted moving average to convert original audio into a handcrafted-like signal. We also annotated VGG sound with caption labels and created a new dataset called VGG Sound Caption. During inference, Draw and Audio can synthesize mixed audio in multiple stages, enhancing its practical application. Our key contributions include the introduction of Draw and Audio, which supports multiple input instructions and generates audio with improved content, timing, and loudness consistency. The Mask-Attention module and Time-Loudness module provide designers with additional control over sound intensity. Our experiments on our dataset and other challenging datasets demonstrate that Draw and Audio outperforms existing methods and has broader applications. Next, we discuss related work on latent diffusion models, which have shown remarkable generative capabilities through denoising processes. The latent diffusion model, LDM, enhances training and sampling efficiency by mapping features into a latent space, reducing computation while maintaining quality. LDM's cross-attention conditioning mechanism supports various generative tasks, including image, video, and audio generation, which significantly inspires our research on video-to-audio generation. Section Summary. In this section, we introduce Draw and Audio, a framework designed to enhance audio synthesis for video Foley by ensuring content, temporal, and loudness consistency through the use of multiple input instructions, including drawn video masks and loudness signals. Our approach leverages advanced techniques from latent diffusion models to improve the controllability and quality of generated sounds, addressing key challenges in video-to-audio generation. Section: Text-to-audio generation. In this section, we discuss text-to-audio generation, which has recently gained significant attention. We utilize diff sound, which uses a discrete diffusion model to create simpler representations of MEL spectrograms, allowing for faster processing. Make-an-Audio improves audio production through a method that combines different concepts and employs CLAP for better understanding of natural language. Tango uses latent diffusion models, while Audio LDM2 enhances audio quality by incorporating Audio May. For our exploration, we choose Audio LDM2 as our latent diffusion model architecture. Next, we look at video-to-audio generation, which shows great promise alongside advancements in text-to-video generation. IM2 Wave uses a transformer model with clip features but has slow processing speeds. Spec-VQGAN generates new spectrograms from a pre-trained codebook based on video features. The Diff-Foley model also uses a latent diffusion model to create high-quality audio and learns features for better alignment of audio and video. In contrast, Sonic Vision LM uses vision language models to suggest sounds that match video content. However, current methods in video-to-audio face synchronization challenges because they depend only on video or text, which limits their ability to capture complex audio-visual relationships. Our method, Draw-an-Audio, aims to generate sounds that match the content, timing, and loudness of input videos. We represent our model as a function that takes conditioning sets and produces generated audio. To fully understand our model, we first outline the basic framework of Draw-an-Audio and then detail the components of the Mask-Attention module and Time-Loudness module. We have chosen the Latent Diffusion Model, LDM, as our foundation due to its success in text-to-audio and video-to-audio tasks. Following Audio LDM2, we use log-MEL spectrograms transformed from audio as input. The LDM learns to reverse the diffusion process in a compressed latent space, which helps reduce computational demands. Initially, we sample a latent feature from real data, then the LDM adds Gaussian noise in a series of steps. The forward diffusion process involves gradually introducing noise, and the final step results in a noise distribution. During training, the LDM denoises and reconstructs the original latent feature from noise estimates. For inference, we generate the initial audio latent by sampling from a noise distribution and using the conditioning sets. We provide multiple instructions in Draw-an-Audio, including text, video, and loudness signal conditions. Section Summary. In this section, we explore advancements in text-to-audio and video-to-audio generation, highlighting models like Diff-Sound, Make-an-Audio, and Audio LDM2, which utilize various diffusion techniques to enhance audio quality and synchronization with visual content. We focus on our model, Draw-an-Audio, which employs a latent diffusion architecture to generate audio that aligns with input videos based on content, timing, and loudness, utilizing a Mask-Attention module and Time-Loudness module for improved performance. Section: Mask-Attention module, MAM. In this section, we introduce the Mask-Attention module, MAM. Traditional Foley methods generate audio directly from video without focusing on specific local details, making it challenging to create sounds that match particular content, such as the sounds of cats in a video. To solve this, we designed the MAM to improve area control. By using prior masks from the video, our model enhances the relevant regions, ensuring that the audio aligns with the content. Before we can use the MAM, we need to obtain suitable masks. Given a text-video pair, where the text represents the caption and the video is a series of frames, our goal is to generate many binary masks that highlight sound-related areas in the video. We achieve this by employing YOLO World to create these masks in real time using an open vocabulary. Since the caption may not work well with the open vocabulary model, we first use a simple n-gram algorithm to extract noun phrases. We then input these phrases into a text encoder, pre-trained by CLIP, to get the corresponding text embeddings. After extracting the masks, we inject the masked video features into the MAM while keeping all video information intact. Given the cross-modal nature of our task, which involves both video and audio, we use CAVP as our visual encoder. Unlike traditional methods, CAVP is trained specifically on audio-video pairs. To effectively combine the masked features with the original video features, we introduce channel-weighted blocks that enhance the original visual features to create a visual condition encoding. Next, we discuss the time-loudness module, TLM. The goal of video Foley is to generate audio that is well aligned in time and consistent in loudness, meeting the needs of Foley designers. We believe that using hand-drawn loudness signals as input conditions can help maintain this consistency. However, training our model with such signals is challenging due to the lack of large datasets with smooth signals aligned with video-audio pairs. To address this, we propose an audio transformation method based on root mean square, RMS, energy, which converts the original audio into human-like loudness signals. We define the audio signal and calculate its RMS energy, which gives a better representation of average loudness than peak levels. To create a signal that resembles a hand-drawn one, we apply adaptive average pooling and exponentially weighted moving average techniques. This process simplifies and smooths the signal, making it easier to plot manually. After obtaining the loudness signal, we use a multi-layer perceptron, MLP, as the signal encoder to map it for training. During inference, Foley designers can manually adjust the loudness of the generated audio. The TLM enhances both temporal alignment and loudness consistency. Further details and visualizations of the loudness signal production process can be found in our supplementary material. Section Summary. In this section, we introduce the Mask-Attention module, MAM, to enhance audio generation by focusing on specific sound-related regions in videos using binary masks derived from captions, and we propose the Time-Loudness module, TLM, to improve temporal alignment and loudness consistency by transforming audio signals into hand-drawn loudness representations. Our approach allows for better content consistency and gives Foley designers the flexibility to control audio loudness during the generation process. Section: Text and Video Classifier Free Guidance. In this section, we describe our approach to audio generation using text and video inputs. During the inference phase, our model, Draw an Audio, generates sounds based on text, video, and loudness signals at the same time. We utilize a dual classifier free guidance strategy to adjust the influence of both text and video conditions. This guidance method helps steer the predicted noise towards a more accurate output by using an implicit classifier. Specifically, we guide the unconditional predictions towards the conditional ones using scalar weights for text and video, which we discuss further in our ablation experiments. For our experiments, we use the VGG sound caption and audio caps datasets. The VGG sound caption dataset includes around 200,000 10-second video clips with captions across more than 300 categories. The audio caps dataset has about 46,000 10-second video clips with natural language descriptions sourced from the AudioSet dataset. We downloaded a total of 223,000 clips for our experiments, as some were removed from YouTube. To evaluate our model, we randomly selected 1,000 clips from the test sets of both datasets, training and assessing our model separately on each. Additionally, we trained on a mixed dataset that combines both sources for practical applications. For data pre-processing, we follow the methods used in Diff Foley. We sample the 10-second video clips at 4 frames per second, resulting in 40 frames, which we resize to 224 by 224 pixels. All audio data is resampled to a frequency of 16 kHz for consistency. During training, we randomly crop video-audio clips to 8 seconds, leading to specific lengths for frames and audio. Our model, Draw an Audio, is based on the Audio LDM2 architecture, and we maintain the same training settings. We convert audio clips into MEL spectrograms with defined MEL lengths and bins. For text input, we use embeddings from the Frozen Clap and FLANT5 models. For video input, we extract features using the Frozen CAVP visual encoder, ensuring consistent dimensions for comparison. For the loudness signal, we compute the RMS energy with specific parameters. The signal encoder consists of trainable MLP layers. During inference, We set the classifier free guidance scales for text and video, and we use the DPM solver sampler with 25 sampling steps. To evaluate the effectiveness of draw in audio, we focus on the V2A generation task, following the evaluation protocols of Spec VQGAN and IM2 Wave. We calculate objective metrics such as Frechet distance, inception score, Kullback-Leibler divergence, Frechet audio distance, and clip score for audio and video. The Frechet distance measures the similarity between generated and target audio samples, while the inception score assesses both quality and diversity. Kullback-Leibler divergence evaluates the similarity between generated and target audio labels. Frechet audio distance is a reference-free measure based on the distribution distance of audio features. We also introduce the clip score for audio-video correspondence, using Wave 2 clip as the audio encoder. We compute the cosine similarity of feature vectors from both video and generated sound, applying a scaling factor for the final evaluation. Section Summary. In this section, we describe our approach for generating audio from video and text using a dual classifier free guidance strategy, which enhances the conditional predictions during inference. We detail our datasets, pre-processing methods, training parameters, and evaluation metrics, emphasizing the effectiveness of our model through various objective measures. Section: Quantitative Results. In this section, we present the quantitative results from the AudioCaps test set, which includes the complete training datasets for each method. Our method, Draw in Audio, significantly outperforms the baseline method while using fewer training datasets. Specifically, we achieve better performance in various metrics, including a decrease in FD, an increase in IS, a decrease in KL, and an increase in carbon monosulfide AV. We also tested Draw in Audio on a larger dataset, VGG sound caption, and trained our model on both datasets combined for improved practical application. Our results indicate that as the amount of training data increases, the performance of Draw in Audio improves further. For qualitative results, we visually compared Draw in Audio with other methods using samples from both datasets. In one example from the AudioCaps dataset, we observed that Draw in Audio successfully generated both quiet and loud sounds with consistent timing, while other methods struggled to produce loud sounds that matched the video's timing. In another example from the VGG sound caption dataset, our method generated sounds that closely matched the ground truth MEL spectrogram, demonstrating greater precision than the alternatives. We also explored the effect of using multiple input conditions with Draw in Audio, which enhances its controllability and user-friendliness. Our comparison of different input conditions, such as text prompts and loudness signals, showed that text instructions had the most significant impact on performance, as our model is pre-trained on the T2A architecture. As we increased the number of input instructions, we observed a notable improvement in our model's performance, thanks to the integration of our proposed MAM and TLM. Furthermore, we examined the importance of dual classifier free guidance scales for sampling from latent diffusion models. Our findings indicated that varying the scales affected the quality and diversity of the samples. After comprehensive evaluation, we set the default scales to 3.5 for text and 4.5 for video. Lastly, we investigated how training parameters influence model performance. Our extensive experiments revealed a direct correlation between the number of trainable parameters and the improvement in our model's performance, suggesting significant potential for further development.